Hello and welcome back to Calculus 3. Looking at a section 12.3, limits and continuity. So, same concepts that we learned in Calc 1 will be now extended to the 3D. We have two independent variables, x and a y, which are controlling dependent variable z. Now, in Calc 1, we described limit as a fancy way, in quotes, to compute the y value of a function. So what we did is, as we approach from the left, we would go up the line, we would go up the y-axis. And if we approach from the right, we would go down the line, down the y-axis. And if they meet at the same value L, we would say that's the limit. So the theorem 2.2, if you care about the exact placement in the book, it said that if the limit x approaches a from the left of the function is the same as the limit x approaches a from the right, the same function is L, then the overall limit x goes to a from both sides, so no plus and minus, is L. Otherwise, limit does not exist. So what was the otherwise case? Well, otherwise case could be a step function or jump discontinuity. So you have something like this, jumps here, and it goes this way. So now, at A, you see that as you go from the left, you have this value here, and if you go from the right, you will have this value here. And clearly red and blue are not in the same spot, therefore limit x goes to a from both sides of f of x does not exist. Now, one-sided limits exist. Both one-sided limits exist. Let's say they're 1 and 2. Okay, blue is 1 and red is 2. It's the overall limit that does not exist because the two one-sided limits gave us different values. So that was the idea of the limit from Calc 1. Then there was that precise definition which stated that for every epsilon larger than 0, there exists delta larger than 0 such that L minus epsilon, right? L f of x minus L less than epsilon equals 2. So we have that definition. Keep in mind that you had the domain to be just the x-axis. So your domain was one-dimensional. If your domain is one-dimensional, a point can be approached only in two ways. You are confined to that one dimension. You can approach point A either from the left or from the right, which gets us to write such a simple statement, because there's not that many choices. But now, in Calc 3, our domain looks like this. This is how domain looks like. You still have one output, right? One-dimensional output. So domain is 2D. So in how many ways you can approach xy? Infinite way. It's no longer approach from the left or approach from the right. I can just do this. And there we go. It's an approach. Some people drive like that. Emily drives like that. So it is becoming very tricky to figure these limits out. We generally fall back to calculating values. And in some sense, the easiest part would be to disprove a limit. So the approach to figure out these limits is, I'm just going to draw a few approaches over here. So we have a whole bunch of different approaches. So how did we find limits in Calc 1? We had graphs, right? So you look at the graph, use your eyes and determine the limit, because we said it was just a y value. We had charts, a table of values. And then we had algebra. Now, what do I mean algebra? Well, you might be able to factor and cancel, you might be able to rationalize, you might be able to do some kind of algebra witchcraft, which would make the limit into an easy problem. Before you do any of these last resort techniques, obviously the first choice is plug it in, because we know that the limit of x squared when x goes to 4 is just 4 squared, which is 16. In the end, limit computes the y value of the function. But the limit is much more powerful than just figuring that out. You see, I can go and just say f of x equals x squared, f of 4 is 16. I can use pre-calculus for this. And that's what I did. I used the pre-calculus right here to compute. The calculus way to compute that would be to actually pick values. Right, so this is the 4 that you want to investigate. So we need 3.9, 3.99, 3.999. This is 3.1, 3.01, and 3.001. That's what I said. Please pay attention. These are all 4s. I'll zoom in. See? Look, 4s. Clearly. So you would actually compute these values here. And you would see that they lead. This one is coming up to 16. This one is coming up to 16. So the answer is 16. Because as you compute these values, they get closer and closer to 16. So now, that becomes our major method to figure out these limits in Calc 3. You would obviously have x and y inputs computing z's, and you just kind of focus on the circle around the point. So what do I mean on a circle around the point? This is your domain again, and you are mapping that into a z. So if you pick a point somewhere, there's going to be this circle with the radius delta around it, and the idea is for this point to map to a point L, which will have the interval around it as L plus epsilon and L minus epsilon, which are those epsilon and delta from the definition. So you would be picking values that are with a distance formula getting closer to the point x, this is x and y, call it AB if you want to, right? X and y going to AB, specific value. So in a 3D world, what can happen? You have a smooth object like this, continuous everywhere. no issues, right? But then you can have an object which does have discontinuity. Well, not this discontinuity. That has the limit does not exist. So something that, well, actually, if I put it this way, has a vertical edge, right? So let's see what is the definition for this, and then we're going to take a look at the problems that we can solve, and those are the ones where we actually just plug in and solve, or when we say that the limit does not exist because two different paths leading towards the same point will give two different answers, which is running parallel to this situation here. You find two different paths that give different value, therefore the original one will not have a limit there. So let's take a look at the definition. So what does it say? The function f has the limit L as Pxy approaches P0, which is x0, y0, or actually, sorry, AB, easier. AB, written like this. If given any epsilon larger than 0, there exists delta larger than 0, such that f of xy minus L is less than epsilon whenever zero less than the distance formula is less than delta. This is the same definition like in your Calc 1, section 2.7, except this one is for the 3D. This is the actual statement, right? Important part. So for any epsilon, there exists a delta that created it, such that these two conditions fit together. What does this mean? Well, they have this picture in a textbook, which I'm going to show you now. And you see this 2 around the value. So you are interested in the limit at the point Pxy, right there. No, you are interested in the point AB. So this point Pxy, which can take on any value for x and any value for y. These are set in stone. A and B are given, like 3, 7. So you see that 3, 7, say, lives on the xy plane, lives on the floor, and then there is the circle around it, delta circle, which creates this 2 around the values for L, which are mapped on Z. So this function, whatever it is, has some kind of surface. When this point hits that surface, immediately gives you the Z value for it. Some people have trouble visualizing that. So let me try and bring this thing on the board, see if we can figure out what's happening there. So before I do the 3D case, I will just draw one more time the 2D case. So I have some kind of function, and for my input A, I will go here and bounce off. So this point is A, f of A, and this over here is just f of A. So those are my y values. Y is f of x. So if I plug in A in there, I'll get f of A. If I pick a different value, C, go up, bounce over, that's f of C, and this is C f of C. So always x comma y coordinate. Here's the x coordinates on the x-axis and y coordinates on the y-axis, and over here x comma y for this point. The same thing is going to happen if you have some kind of a shape. I'll put the plane here, and then in the xy coordinate plane, I come up with a point AB. That point AB will go up or down, whatever the shape is, and bounce off of it into Z. So this point is A, B, f of AB, and over here is just f of AB, because that's what Z is. Z is f of x, y, and if I use particular xy, AB, like 1, 3, then I put AB there, or 1, 3. So, again, if I have a plane, which is now 3D, you have a plane that is 3D, and that lives in this 3D space, and the floor, take this desk over here. This desk is the xy plane, so I'm measuring my x's, my y's, and then Z is going to stick out. And I have this plane. So if I have a point, and I'll extend that point, so there is a point on the desk which will extend up. So the point AB is in the domain of the plane, right there, and there is a surface over here of some sort. So this AB will hit the surface, and at the elevation at which it hits the surface is where I read the Z value, let's say number 7. Okay? So I will just go parallel to the XY surface to the axis Z, which is here, and I will just read that that height there is 7. Make sense? Now take any kind of a shape. Unfortunately, there is no range, so no one has the umbrella here. But if I'm to open the umbrella, umbrella would be your parabola, this guy, right? If I put the umbrella upside down, it will look like this. So now, when it looks like this, it still doesn't matter. If I pick a point here, AB, it will go up, it will hit a surface of this somewhere, we'll just go across and read the Z value off of the Z. So it has to hit somewhere, right? Because if it's in the domain, the shape will be somewhere above or below. That's another part where it stumps sometimes. The function lives above or below the domain. Domain is the x-axis. So for square root of x, right, your domain for square root of x is all values larger than 0, including 0. So the portion, the positive values on x-axis are in the domain. So if I have a 3D object which is finite, living over this infinite domain, Well, the shadow of this object onto the xy plane is the domain of the object. You cannot plug in a value that will never bounce off of the surface to the z-axis to read it. Just like here, I can't pick -3, because if I extend -3 infinitely up and infinitely down, it's never going to cut this one to give me the reading. If I pick +4, it's going to go up and bounce into 2. Square root of 4 is 2. So that's the idea of also in a 3D. So now when we're looking at the limit, this point AB is where we are looking for the limit. We let this xy wander around and keep bouncing off of the shape, giving us all of these values. As the distance, and that's why you have a distance formula here, as the distance between these two squeezes. Now I don't care if it's going to squeeze in a straight line or if it's going to spiral in. I don't care which approach it has. If it gets close to this, and all of the points that we're getting on the z-axis are pointing towards the same L all the time, that's the limit. If some of them shoot off to infinity, some of them shoot off to -infinity, some of them are 3 or 5, in that case, no limit. So they all have to converge into a single L. And the way you are achieving that, you're calculating by hand, is that you are kind of picking the values that are constantly getting closer to AB, and you keep computing Z, keep computing Z, keep computing Z, and you're just picking random points that are closer and closer and closer and closer and closer. And the trend will show that that's the limit. That's the limit. Now, with that being said, what's happening when we don't have a limit? So, as I said before, if we have a random point somewhere, I can approach that through, I draw a linear line, and if I draw a linear line to this point, right, AB, that I'm trying to find, that would be a way to approach it. Now, this line has some kind of y = mx + b formula. Once I plug that in, I eliminate the variable. It's awesome. And I can just look at the one-dimensional input because I just made up a relationship between x and a y. But that's not enough for me to claim that the limit exists, because remember, I can spiral in as well. It's a little bit more complicated formula. So what I'm going to do, I'm going to say, if we are able to find two paths which lead to different L, limit at AB does not exist. So that's the flip side of the theorem from Calc 1. And let's take a look at some of those. Now, the properties of limits and all of the other stuff, that's the same like in Calc 1. If you're interested, on page 887, you have the chart which says that the sum and the difference and the product and the quotient and the scalar multiplication and squaring and exponentiation, they all lead into the same value, they all have the same conclusions like your 2D limits from Calc 1. Okay, I'll have to define that. All right, so before we get into these non-existent limits, we have to understand a tag about interior and boundary points, and then open and close sets. A lot of definitions later on in Calculus 3 will depend on you understanding this stuff. So what is the interior point and what is the boundary point? First, here is a potato. It's the asteroid, fine. Just asteroid. It is the arbitrary function, okay, the domain. It's arbitrary domain, 2D. And I have 2 points P and Q. And I put these circles around them. These circles we call disks. So one of these 2 points is interior point. The other is the boundary point. Now, when you're looking at the picture, it's clear which one is which. Now we're going to write mathematical definition for them because that's what we do. So let R be a region in R squared, so in 2D. An interior point P an interior point P of R lies entirely within R, which means that it is possible to find a disk centered at P that contains only points of R. Now, radius is allowed to be as small as you want it to be. It can't be 0 because it has to contain some other points in there. So if the point is interior point, you are able to draw a disk around that point P, and all of the other points, all of these other points, right, are also in R. Now, to contrast that, look at Q. There is no way that you can draw a disk on a boundary point so that all points are at P, at R. There's no way. So these points are going to be on the interior, and these are the exterior. Because this has to be the center, and you have to have a radius. Now, it doesn't matter how small you make this radius, how small it is. If you make really small, right, when I zoom out, you see, that's much smaller. I can make it even smaller. It doesn't matter how small you make this, it will always have the points inside R, which is the region, and outside R. So that would be definition for the boundary point. So boundary point is the point which has that behavior. Now, why would this be important? Well, remember that you also had those crazy points when you had limits in Calc 1. 1 over x. Right? 0 is a crazy point there. Because 1 over 0 is undefined value. So a boundary point Q of R lies on the edge of R. Lies on the edge of R in a sense that every disk, and this is important, like every disk, centered at Q contains at least one point in R and at least one outside the R. And that should be clear from the picture. And now with these definitions we can define open and closed sets. So a region is called open if it consists of interior points, and a region is closed if it contains all of its boundary points. So now open sets only have interior points, which makes sense, right? No boundary. Open set. Think of the infinite floor. If this floor is to extend infinitely in all directions, there will be no boundary to it. So we call that an open set. Or why is open? You can go forever in any direction you want. It's open. There's no constraints. Closed set has a boundary, and that boundary is what closes it. Now we are in a closed set here because you go to the wall and that's it. You can't go any further around. Think of this black stripe here. What the hell is that called? Whatever it's called. It's not really mold. It's a piece of rubber that acts like a molding, right? It's in a house, a piece of wood there, right? So, but okay, let's black stripe. All right. So this black stripe would be a boundary, right? You can't go past this black stripe. Oh, yeah, we do have an opening here, but that's right. So closed set contains all boundary points, right? And of course there are interior points inside, but it's enough for us to say that it contains boundary points because common sense is that everything else inside is the interior point.
What if you only have one boundary point? Is it still closed?
You can't bound anything by one point, right? You are talking about a two-dimensional region, and a point is a location, so one point cannot really bound anything. You have to have a line, contour of some sort. You can't have a single point. Do that. That's why it says contains all the boundary points. Can't enclose the region with one point. Now, what kind of mathematics comes out of this? Well, now we can have limits which will have zeros in denominators, let's say, and we can look at existence or non-existence of those limits. So in some cases, just like in your Calc 1, you might be able to perform some kind of a witchcraft and cancel those denominators. So let's say you have limit xy goes to, I don't know, 2, 0. And the function is x squared plus 3x. No, that's bad. X squared y squared plus 3x y over y. In this case, not a problem. You can factor out y. It will cancel the denominator, and then we can just plug in. Remember, these limits now must behave the same way as your Calc 1 limits in terms of calculating, that you should first try to plug the values in. If you don't have zeros in the denominator, you're done, because you can just compute. Remember, limit of x squared as x goes to 3 is 9. That's it. So in this case, if there was no y in the denominator, you would just plug in 2 and 0 everywhere, and you would just get 0 everywhere, right? But now, don't forget to copy the limit. You have to keep copying the limit until you actually use it. You factor out y, you get x squared y plus 3x divided by y, and these cancel. See, now you can just plug in the y equals 0 will kill the first term, but the second one will survive, and the answer is 6, because 3 times 2 is 6. Now, physically, does this point exist? The answer is no. It will be the open circle on that surface. Think of a piece of clothing with a hole in it, okay? Or a button or a bug ate through or whatever. So, or just simply take, oh, here, there you go. See this? The 3-punch? That's it. So, if this surface was, let's say, this surface like this in space, that limit 6 would be this hole here. You cannot have material shape. You can't have the meat there, all right? Because it had a y in denominator in its original state. Because the original function, before you perform cancellation, is the actual shape and the object. Once we started calculating, we were lucky that we were able to factor and cancel. So we found that this is 6 feet tall, right? Let's say at 6, that's the elevation of this point, even though there's no point there. There's nothing at that. Thank you for handing in homework, Sam, because that was, right, a big part of the instruction now. Now, in some cases, you will not be able to cancel. They will stay. The zeros in the denominator and so on. Then we try to find those paths and prove that the limit does not exist.
How
Matt?
do you notate open versus closed?
I'm sorry?
How do you notate open versus closed limit?
There's no open and closed limit. There are open and closed sets. Well, the open and closed, and we're going to put the R's and things. So we'll get there when we in theorems and definitions we just say over the open set over the closed set. That's what we say. Yes.
But this limit, which computed this sets, still is not real. It still doesn't exist.
The point doesn't exist in a physical realm. The limit is 6. The limit is 6. So if the point existed, it would be on elevation 6. Okay? It doesn't exist. But if it existed, and it doesn't exist because it was over y, y0, and the function explodes at that point. It was the difference when you were looking for vertical asymptotes in Calc 1. You had the problem of x squared minus 25 over x minus 5 and x squared minus 25 over x plus 5. There's the third one. Bless you. So, gotta wait for the third. Right? And she will. So if x goes to 5 in this case, right? You see 5 minus 5 is 0.
Yeah.
It's not good, right?
Yeah.
But if you factor and cancel, you get x minus 5 to cancel, and you're left with x plus 5, so the limit is 10. If you are to graph this, it will actually be the linear line x plus 5, so it will look like this with the open circle at 5.
Yeah.
But if you have this situation here, and you have limit, and again x goes to 5, no, negative 5. No, it's going to be the same. I wanted the vertical asymptote. Oh, no, I just need the same function. Just need the same function. X minus 5, now when they cancel, oh no, I need it upside down. X minus 5, x squared minus 25. There we go.
Yeah.
So now when they cancel, and the plus. So now when they cancel, what's left? 1 over x minus 5. Still a problem.
Yeah.
So this one will, minus 5, will graph that way.
Yeah.
Right? So this is a vertical asymptote, and this is an open circle. So same over there, we got it 6. So you have 2, 0, 6, open circle. On the surface. Think of the hole, right? It's a hole. Yes? Well, this is all done at the point. Can't have a radius. This is a point. You're doing it at the point. Yeah, it's done at the point. Because anything more than a point, you're cutting open a region. And then you go back to open and closed sets, which later on will have the regions, which will be connected, simply connected. You'll see the whole spiel of those things. I don't think till chapter 13. And we'll have the regions and fun with that. Okay, so now we're getting to these interesting problems where we can't factor, we see 0 in denominator, we can't factor. What time did class end, by the way? 8:20? So well, we have 7 minutes left, and then another 20 after that. I know. So limit xy, I should have gone for 2 minutes left and then 25 after that, but I didn't. So be happy. Here's the problem. X plus y squared over x squared plus y squared. Now, guys, the most important part here is not to get discouraged. Keep pounding on the problem until you get it. All right? The first thing you try is to plug in. If you get 0 in denominator, it's bad. Then you try to factor, cancel, rationalize, do something with algebra. If that doesn't work, then you apply the procedure to find 2 different paths that will give you different limits. So now what you are looking here is you plug 0, 0, and clearly in denominator 0 squared plus 0 squared is 0. So that's bad. Now there's no factoring here of any kind that you can perform, right? Because nothing factors. And then also, in addition to that, you also have no square roots, so no rationalizing, right? So none of those things work in this case. So what do? Well, we try to find an approach. which will give us different value, and we're still approaching 0, 0, but we are approaching from different, let's say, approach from different angles, okay? So if you look at the domain, this is my target point. Now I can approach that on a line y equals x. Now once I put that line, my number of ways to approach went from infinitely many to only 2. I can approach this way and that way, right? And that's going to give me some kind of a limit. So now let's see what's happening here. Look, my line is now y equals to x. So if it's y equals to x, well, I can plug that in and reduce number of variables from 2 to 1, and the whole problem collapses to a calculus 1 problem. So when I use this, right, plug in, what do I get? I get the limit, because I'm only going to have x's left. It's just x equals to 0 now. And y is replaced by x, so I have 2x squared divided by 2x squared, like this. Now I hope you guys see that the limit for this is 2, because you have 4x squared divided by 2x squared, and that cancels to 2. So we are thinking that the limit might be 2, right? But let's try a different approach. You can use any function under the sun that goes through 0, 0. You can use e to the x minus 1. You can use sine x. You can use cosine x minus 1. You can use whatever is going to go through the origin. But let's just use y equal 2x, because that's easy. So now use y equals 2x. Now you plug that in, and if y is equal to 2x, we get limit x goes to 0, 2x plus with 3x squared divided by, is that 5x squared on the bottom? So it's 9/5. You see that? At the same point, if we approach from one way, we get limit is 2. We approach another way, we get 9/5. That's not 2. So, no limit. Does not exist. Awesome, right? So I used 2 different functions. They were both linear. To come up with this. All right, let's do another example. I'm gonna go pull one from the homework. Here. So try this one. Zero, zero. Y cubed minus, x cubed minus y squared divided by x cubed plus y squared. So look for 2 paths. See what happens. I'll be right back.
2D.
You figured it out? Is there a limit or no limit? Actually, I brought chocolate for all of you. I just ate everything. What happened?
Oh, I was just raising my hand.
Yes.
Just to raise it.
Okay. Now, what's the answer to the question? There is no limit?
There is a limit.
There is?
Yeah.
How do you know?
Because,
So what's the limit?
yeah.
And you checked everything.
Well, if you set y equal to any variable times x, then the m will cancel. Well, the any variable will cancel will equal to -1. But everything will cancel except for.
Okay. So that's a cool thing to try. Let's try and use infinitely many approaches at once, this mx. If the answer depends on m, then obviously you pick m1, the answer is one way, the m is equal to 2 would give the other way. So let's see. What do I get? Limit x goes to 0. I have x cubed minus m squared x squared divided by x cubed plus m squared x squared, which is limit x goes to 0. We factor out x squared, numerator and denominator, and they cancel. So we are left with x minus m, x plus m. Now, what happened? It's m squared, yes, that's what I said. Please pay attention. So now, when we plug x equals to 0, we get -1. Now, this means that every time when you can pick anything, the limit will always be -1. Great. We cleared all of linear functions. Now what? X squared, y squared. I know there's infinitely many options. Nope. So now, y equals x squared. If we get anything different than -1, it's done. So limit x goes to 0. We have x cubed minus x to the 4th divided by x cubed plus x to the 4th. We get -1 again. Right? No, we get 1 minus x. Oops, I forgot the limit. That's -5. You can put m. Try all. Yes, you can m. But since I already have this one as for all linears, as long as I find one that it's not -1, I'm done. Factor out x cubed and cancel. We get 1 minus x, 1 plus x, and we get +1. So we found that on our domain, if we approach, let's say, y equals x, the limit would be -1, and if we approach y equals x squared, limit would be +1. So no limit at 0, 0 does not exist. We were able to find two paths. Do you want one more of these? Now we have a minute left, and then another 5 after that. No, oh yeah, continuity. Who said continuity? I said continuity. So we do exactly the same thing like in Calc 1. Same 3 rules that you have to check, and if any of the 3 rules fails, the function is not continuous. Rule number 1, f of a, b must exist. Rule number 2, limit of f of x, y, as xy goes to a, b, must exist. And 3, limit of f of xy as xy goes to ab must be f of ab. These are the same rules like you had before. I said there was no y's and b's in it. If you take y's and b's out, it's going to be the same stuff like in Calc 1. If any of these fails, the function is not continuous. Now, this is continuity at the point AB. Continuity at the point AB. Global continuity function z equals f of xy is continuous on its domain, entire domain, if it is continuous at each point in that domain. So that's the global continuity. All of the other rules, sum of continuous functions, difference of continuous functions, multiplication of continuous functions, function composition of continuous functions, they all hold still. That's, across dimensions. So if you combine 2 continuous functions, you will get continuous function back. You have to be careful with division, right? We know that 1 is a continuous function, x is a continuous function, but 1 over x is not. So division, you have to be careful with division. How would you answer the question if h of xy is continuous function and you have ln of x squared plus y squared plus 4? Well, you know that the inside is continuous because it's polynomial, right? And you know that ln is continuous on its domain, and you know that the function position is continuous. So you actually write a paragraph. So this question is answered, right? So is it continuous? The answer is yes, because, and then you write the paragraph. X squared plus y squared plus 4 is continuous on the entire r squared plane logarithmic function is continuous on 0 to infinity by theorem function composition of two continuous functions is continuous function. So there you go. That's actually what you write. That's the answer, the paragraph. Functions of 3 variables, functions of 16 variables, and so on, all behave the same way. The number of dimensions does not matter. So you count how many independent variables you have. There will be one dependent variable which is produced by combination of those independent variables, and all of the rules from this section hold. All right, so that's it for this time. We'll continue on Wednesday. Don't forget about the exam next week.